So it'll be a Blackboard style talk. So you can see it, right?
Yes. So you're from the Dutch side of Belgium? Oh no, the German side, Dutch.
The Dutch side. I'm from the Dutch side of Belgium.
But you also speak others.
I mean, I learned a bit in school, but in practice, not really. Already write the title. Remind me, where do you get PhD? Max Planck? Yeah, Max Planck and the Technical University of Munich, kind of combination of it. but you can just say Max Planck. Yeah.
Maybe let me press the recording.
Mm-hmm.
Welcome everyone. Welcome to Harvard CMSA Quantum Matter in Math Physics Seminar Series. Welcome iedereen. Ik ben blij mee, Ruben. We zijn blij mee dat Ruben het woord is. Ruben previously studied at the Pyramid Institute and then got his PhD at the Max Planck Institute and Technische München in Germany. And currently he is a postdoc fellow at Harvard. He will be speaking about very exciting topics on Higgs equals to SPT. And let me remind the audience, please feel free to interact with Ruben, ask questions during the talk. And let us directly welcome Ruben. For yours, please take over. Thank you.
Thank you very much, Juven. Also, thanks for the invitation. And yeah, thanks to all the rest of you for tuning in. And yeah, let me repeat what Juven just said. So please, let's make this as informal as possible. So as you see, it'll be a sort of Blackboard style talk. So please interrupt at any moment if you have any questions or concerns or comments. So I'll clearly, as the title suggests, I'll be trying to connect two seemingly distinct concepts. Individually, they have been well explored. On one hand, Higgs phases, and the other hand, something called SPT phases. I'll be introducing both of them shortly. But before I start, let me point out that it is a collaboration with several other people. So first I want to acknowledge them. So really, Ryan Thorngren has really been key in much of what I'll be talking about today. So he, of course, was a postdoc at the CMSA until a few months ago, and now he's living the good life as a postdoc at KTP. Also, Umberto Borla, a PhD student at TUM, did the numerical study that I'll be mentioning. And then the other collaborators involved are Sergei Moros, Sergei Moros, who is at Karlstad University, Tibor Rakowski, who's a postdoc at Stanford, and Ashwin Vishwanath here locally at Harvard. Okay, so with that, let's get started. So clearly, I'll be talking about gauge theory, and I don't think we need to be convinced of how important or relevant gauge theory is. So I won't give a general introduction to that. Just to the one sentence summary essentially. As we all know, I'll be talking about something where there's a sort of local gauge transformation or local symmetry, where matter fields don't just have a phase invariance, but actually a local phase invariance. And of course, that means that the theory has some kind of gauge field, which also transforms under some arbitrary choice of gauge transformation alpha. And then naturally, the physical gauge invariant quantities of the theory will be combinations of these two objects to make gauge invariant quantities. Okay, of course, the topic of gauge theory is incredibly broad and is relevant for many different things, right? From fundamental physics to emergent descriptions of many body quantum phases. And it has been understood that gauge theory has many possible phases that it can be in, because essentially gauge theory is just specifying a sort of Hilbert space, and then we can explore what phases of matter one can have in that setting. And in this talk, I'll be focusing on one in particular. Let me just quickly check. I want to check, yeah, can you hear me well? Just because I know sometimes I have some mic problems, but can I just quickly check if it all sounds good?
Yeah, it's fine.
Okay, awesome, thank you. So the Higgs phase essentially one characterization is that this matter field phi that I just mentioned condenses. It's a condensate of phi. Now, I'll be talking a bit more about what precisely that means, but intuitively, it's similar to, say, a Bose-Einstein condensate of a field, but of course, the subtlety is that now this field is charged under some gauge symmetry, so that makes everything a bit more subtle. And then indeed the question is raised, what precisely is the nature of this Higgs phase? And one characterization one often hears is that it essentially spontaneously breaks the gauge symmetry. But this is not really a very satisfying characterization. Of course, on the one hand, gauge symmetry cannot really be spontaneously broken, if not just for the fact that it's not, really physical, right? Usually said as some kind of redundancy in description. And there's even more concrete theorems like Illuster's theorem, which would argue against the possibility of breaking a local symmetry. But it seems like a useful fiction that is often used, right? If you open up a standard textbook, one might encounter one of the paradigmatic models, so the Abelian-Higgs model, just really in some sense the simplest example, perhaps, and the field theory context for what a Higgs phase is. So the Lagrangian has some covariant derivative here involving gauge field for some matter field, and then some potential, and then some term, some dynamics for the gauge field. And if we didn't have the gauge field, and this potential was the usual Mexican head potential, right? So something like this. Let me just try. So right, usually we would know that if we start with some field at 0 expectation value, it in the ground state, it will prefer to spontaneously break the continuous rotation symmetry in phi space and settle somewhere in a saddle point. But that at least is the case without a gauge field. But now we're coupled to some gauge field, defining the Abelian-Higgs model. And then the question becomes, what is really the nature of the resulting phase of matter? And what is sometimes said is, okay, it's a bit subtle, but if we're allowed to do gauge fixing, in particular something called the Landau gauge, then it really suddenly looks like conventional symmetry breaking. In particular, one has long range order and something that looks like a conventional order parameter. I think one of the first proofs I'm aware is by Kennedy and King in the 80s. So at least in this gauge, it looks like there's some local order parameter, but of course it's subtle because obviously we fix the gauge and it corresponds to something non-local before gauge fixing. So even though it looks like symmetry breaking in the gauge fixing, it doesn't really clarify what the ultimate nature is. And indeed, there are gauge invariant accounts of this Higgs phase, but those gauge invariant accounts ultimately don't really answer the question of what is it, other than showing it's not really symmetry breaking. So this is one viewpoint, that is, some notion of breaking the gauge symmetry in quotation marks. Another viewpoint is that the Higgs phase is essentially it's nothing much. There's nothing much to say about it, because ultimately it's not really a phase of matter at all. So this traces back to some seminal work by Fradkin and Shenker in the late 70s. 1979, and at least they considered, well, they considered various cases, but what I want to discuss now is matter which transforms under the fundamental representation of the gauge symmetry. And what they discovered is that, okay, so let me be just a bit qualitative in this introduction. So they considered a gauge theory which has roughly two axes. And in some sense, one axis parameterizes how strong the matter fluctuations are. So later we'll see concrete model where this can be a bit more precise, but let's keep it intuitive for now. And the other axis, in some sense, fluctuations of the gauge field, or we could say fluctuations of magnetic excitations, magnetic fluctuations. And if both fluctuations are small, we're stabilizing the so-called deconfined phase of the gauge theory, where gauge particles can move freely. Deconfined phase. And in modern language, at least for discrete gauge groups, we also call this the topologically ordered phase. But if matter fluctuations are very strong, they can cause condensation, right, as the Higgs condensate we just talked about. So over here, we have a regime that we can label the Higgs phase, as say approximately described by the abelian Higgs model, for example. And there will be some phase transition as we tune along this axis. On the other end, on this axis here, it's kind of similar, but for magnetic fluctuations instead. So over here, magnetic fluctuations in some sense condense, which means that the particles that break non-trivially with it, which are just electric charges, are confined. So this region is sometimes called a confined phase, which also has some phase transition. And now what this seminal paper showed is that actually the Higgs phase and the confined phase are the same. So there's some gapped path that adiabatically connects them. Of course, the deconfined phase is still separate, so there's some dome like this that separates the deconfined phase from the rest. But it looks like the rest is just some short-range entangled phase, and perhaps there's nothing much to say about it because it's all just one connected blob. Okay. And so in this talk, I'll present an alternative viewpoint or a complementary viewpoint, which is that the Higgs phase can perhaps best be thought of as a symmetry-protected topological phase, or SPT in short. Now, naturally, before I try to explain how those two are connected, let me very briefly review or introduce you to this concept of SPT phases, so we're all on the same page.
Let me make sure something, Ruben. When you use this qualitative diagram, the qualitative diagram, is that still precise? The matter fluctuation will be some phi field minus the expectation value of phi, and take possibly the square and taking expectation value, something like that again?
You're talking about an order parameter, or?
Yes, I just want to make sure what's the physical quantity you are considered to be more precise about the two axes. Is that
you mean like what is the tuning parameter in the Hamiltonian?
No, just the even physical quantity. Like, is that B minus the expectation value of B B minus expectation value of B for the magnetic fluctuations, and for the phi is just phi minus the expectation value of phi, and possibly take some square or something.
It sounds like you're talking about the order parameter. Is that correct? You're asking what is the order parameter carried?
Yeah, what's the macroscopic parameter you are tuning in the diagram?
Yeah, so it depends a bit on later I'll be talking more explicitly about a lattice model, and then we'll literally be seeing that, for example, this is characterizing the hopping of matter on that lattice. So it's basically the dynamics of the matter fields. So if this axis is tuned to 0, matter doesn't move. And as we tune this axis, there's some hopping, like C dagger C, if you wish, or coupled to some gauge field. And then this is analogous for the movement of magnetic fluctuations. But I'll be more precise later, but does that already, is that okay for now?
Sure.
Yeah, thanks.
But how about maybe in terms of physical or experimental observable? Those
yeah,
are
so
my
order parameter. Yeah, that's kind of a question a bit. What is the order parameter here? Well, I'll return to that as well. But in a sense, what is a good order parameter for the Higgs phase is a whole branch of the literature, and it connects very much to what I was just talking about here in the previous point. That, for example, on this axis, you have extra symmetries which allows you to fix a Landau gauge in which it looks like a local order parameter. But I mean, the question of what is the order parameter is a good question. I'll address that more as well later. But in some sense, there's not really an order parameter. That's kind of the part of the story here, right? Is that it's continuously connected anyway. So clearly, there's nothing, well separating these regimes. If you see what I mean. But intuitively, like, or in some limits, you'll have this order parameter essentially in some gauge fixing over here. But it's not clear how perturbative or robust that is a priori.
Okay, thanks.
Okay, thank you.
As long as you
Can
make
I ask a follow-up? Where would the long-range ordered phase be here on this diagram?
It's this by long range. Sorry, can I just check when you, oh, do you mean long range entangled? That's what I presumed you meant, but maybe you meant
more like symmetry broken.
Oh, well, by symmetry breaking you mean what is usually called symmetry breaking here?
Yeah.
Yeah, that would be maybe this axis.
Okay.
The point being, this Landau gauge doesn't exist in general, actually. If you have too many gauge fluctuations in some sense, it's not well defined. But on this axis, you can define a Landau gauge. And in that gauge, this phase looks like symmetry breaking.
Okay.
But I'll try to make the case that it's not really symmetry breaking. It just kind of looks like it in a gauge. So 1 second. So, okay, thanks for the questions. So a quick definition of an SPT phase. So this notion of SPT phase, as far as I'm aware, originates from the condensed matter community, where it's used to describe how to say much more everyday systems compared to gauge theory, but it's quite a general concept that's more generally applicable. So let me review quickly one possible definition. So it's a definition of basically the ground state of a many-body local Hamiltonian. So we say that the ground state of a Hamiltonian H, so H is some many-body system, say some spin system, for example. We say it is a non-trivial SPT phase. I will drop the word non-trivial throughout. When I say the word SPT phase, I'll mean it's a non-trivial one. Protected by some symmetry group G, if it satisfies the following two properties. Firstly, there exists a path of local gapped Hamiltonians that essentially trivializes it. This makes precise that it's in some sense what's sometimes called a short-range entangled phase. Such that, so suppose we have our original Hamiltonian here in parameter space, and there exists a path in the space of Hamiltonians labeled by some continuous parameter lambda, such that we can preserve the gap of the many-body ground state and arrive at a Hamiltonian whose ground state is a product state. Right, so to just zoom out for a moment, what this is saying is that one can disentangle the ground state without going through a phase transition. Okay, so this is sometimes called short-range entanglement. But the second property is such a path does not exist if we want a G-symmetric path, if H of lambda is G-symmetric. So if we don't care about symmetries, we can remove the entanglement. But if we enforce certain symmetries of the state, then the entanglement is protected. That's basically the definition of a symmetry-protected topological phase. So maybe it's a general definition. So for those of you who are perhaps not so familiar with it, let me quickly give you some standard examples. The famous and historically first example is something called the spin-1 Heisenberg chain. So it's just a lattice model of quantum spin-1s that are coupled by the so-called Heisenberg interaction. And it was realized in the 80s by Haldane that this is a gap, that basically there's an energy gap above the ground state, and subsequent studies showed that the nature of the ground state is a non-trivial SPT phase. For example, protected by, as long as you preserve spin rotation symmetry, there's no way of removing the entanglement of the ground state. A more modern example, and perhaps a bit more minimal, but kind of closely related, is something called the cluster chain, introduced by Briegel and Rausendorf into early 2000s. And it's also, this is actually a spin-a-half chain. Oh, someone raised their hand, I see.
Yeah, I had a question, which was, at least intuitively, it makes sense to have a definition in terms of this space of Hamiltonians, but that seems like a very complicated space with very interesting topology. When you say that the spin-1 Heisenberg chain is an SPT, is there a proof by considering all such gapped Hamiltonians?
So it is true for that space, but maybe your question is, how could you possibly have such information about that whole space? Or
Exactly.
Yeah. That's a good. It's a great question. So indeed, it's quite non-trivial. Like there have been a lot of developments over the past decade or two, but people have figured out basically discrete invariants that cannot possibly change across such a path. And hence, for a given model, one can calculate it, sometimes analytically, sometimes numerically. And if that invariant has a non-trivial value, then that basically rigorously shows that you cannot possibly deform it to a product state because a product state cannot have that non-trivial invariant. There's various levels of rigor that have been applied to this, but it's quite well established, I would say. Does that answer your question?
Yep, thanks.
Yeah, thank you. So I was talking about the cluster chain. So this is a three-body Hamiltonian. So what it loses in physical relevance, it makes up for in solvability, in the usual story. And so I'm using, in this talk, I will use X, Y, Z to denote spin-a-half Pauli matrices. It's perhaps one of the greatest contributions of the QI community. But it's, right, so this is a three-body Hamiltonian, and it particularly has a Z2 times Z2 symmetry, given by spin flip on odd sides and even sides. And basically has been rigorously shown that as long as you preserve these symmetries, the Z2 times Z2, there is no way of removing the entanglement in the ground state. And this is actually related to having a non-trivial order parameter. And unlike symmetry breaking, SPTs have non-local order parameters. So for example, has been figured out that the ground state has long-range order and something that looks like this. So one, I just mean the identity matrix, and I'm leaving then basically I'm leaving spatial indices implicit because I just notice the site n plus 1, n plus 2, etc. It's all neighboring sites. And no matter how long you make the string, this is non-zero in the ground state. Forgive me for forgetting the reference for this in a moment. And the reason this is a non-trivial string order parameter is basically the structure it has is the following. You see it has this string. It's like a string operator made up of, say, one of the two symmetries, depending on whether I started on odd or even sides. Let's say this is a string associated to this symmetry, X on every odd side. And crucially, the claim is it only has long-range order if its endpoint is odd under the other symmetry. And indeed, we see that suppose X's were on odd sides, you see that Z is odd under spin flip on the even sides. And this is actually one of those rigorous discrete invariants I was just mentioning. And you can say that in trivial phase cannot possibly have this property. So more generally, this is pointing towards a general mechanism for creating non-trivial SPT phases, which is sometimes is what I just discussed is phrased as a condensation of decorated domain wall operators, or a condensation of these guys. So this is, as far as I'm aware, first introduced by Chen, Lu, and Vishwanath in 2013. So these words, they might sound a bit complicated if you haven't heard of it before, but it's essentially what I just said, that one of the symmetries, basically the disorder operator associated symmetry, is condensed, it has long-range order, but only if its endpoint is decorated by something that's charged under another symmetry. And that's kind of a general mechanism for SPT phases. And maybe some of you have heard of topological insulators. It is basically another example. It's been explored in both 2D and 3D. Yes, there's another question.
Yes, coming back to your cluster model, are the polymatrices here that represent spin 1/2 objects?
Correct.
So what about the time reversal symmetry of H?
You're asking about a time reversal symmetry?
Yes.
Well, yeah. So if you have spin, so it doesn't have spinful time reversal symmetry, right? If you invert the sign, it's not, but it does have complex conjugation symmetry. And that can also protect an SPT. But is that the question, or?
Well, I'm perhaps more like what's the physical realization of that model? Like typically in physical systems, you'll have H would be invariant on the time reversal symmetry. So is there physical motivation for that model?
Yeah, that's a good question. It won't really be the natural Hamiltonian of any solid state system. It does have relevance for the relevance is that it's easily created by doing simple gates. So it's more relevant for the quantum computation or quantum information literature, because by simple two-body Ising gates, one can kind of construct it from a product state. And so it's useful in that context, but it's not going to be the Hamiltonian of any kind of solid state system in any natural sense, I think.
Okay, thank you.
Thank you. Okay, so there are some examples, and of course, the key consequence that got people interested is that this definition actually implies non-trivial edge modes. So what this means is that either in the presence of boundaries, it has some ground state degeneracy, or it has some gapless edge modes. So it's kind of a non-trivial consequence of having this entanglement. And maybe one last thing to quickly mention before I move on back to the Higgs phase, which is kind of a historical fun fact, is, I'll just quickly say this and then I'll take the questions, is, so this concept of SPT phase, I think, was basically formalized by Jacques Van Wen and collaborators, say in late 2000s or so. But the examples, like spin-on Heisenberg chain, is much older, like say this is 1980s. So there was a long period of time in which people knew some limited examples, but didn't have the full description of it. And instead, people discussed it as a sort of symmetry breaking, but in non-local variables. So it's something, it was back then called, so here a historical factoid. It was sometimes called hidden symmetry breaking. So people realized that you can do a certain non-local transformation of your system, and then it looks like symmetry breaking. I think this was introduced by Kennedy and Tasaki in the 90s. And it kind of works, but it's somehow not the most direct physical interpretation. And since then, this concept of SPT phase has emerged, which obliviates this need for hidden symmetry breaking. The reason I mention it is that I would argue it's kind of similar for our understanding of the Higgs phase. It's true that in some limit you can kind of pretend it's symmetry breaking after doing some non-local change of variables. But ultimately, the nature of the phase is different than some short-range entangled phase corresponding to an SPT phase. Now, I think there were some questions. Please go ahead if there are.
Yeah, I had a question, which is, you suggested that the edge modes have to be gapless, but you could have a topological phase with a topological boundary to the vacuum.
Great. No, that's a great point. Yeah, I agree. I was being a bit too rash there. So you could have topological order as well. So basically something non-trivial is living on the edge. Yeah. Was there another question? I thought there was 2 hands raised. Maybe not.
Chicago group.
Sorry?
The Chicago group, yes. I think they have a question.
Or maybe it was from before and maybe they didn't.
No, I think I lowered their hands already. Anyway, that's fine.
Okay. All right, good. So that was a quick recap of SPTs. So let's go back to this main claim of this talk, that the Higgs phase is such a type of thing. And naturally, the next question is then, okay, clearly the definition of SPT phases refers to symmetries that protect it. So what symmetries are we talking about? So let us turn to the topic of symmetries in gauge theories. And this actually ties into the fact that in some sense, this kind of main claim of this talk is not really coming in pure isolation, one way of thinking about it is like a next installment of a previous a change in perspective of the deconfined phase of a gauge theory, right? So traditionally, when people started thinking about the deconfined phase as kind of a many-body phase of matter, let's say with topological order, it was pointed out that it really seemed to be beyond this kind of Landau framework of symmetry breaking. There's no local order parameter that distinguishes topological order from a trivial phase. But since then, in more recent times, it has been realized that you can actually describe the deconfined phase as an example of Landau symmetry breaking, but for a much more subtle notion of symmetry, which is so-called higher form symmetries. So, and well, the concept of higher form symmetries, has a long history. But I think the main paper that brought it to many people's attention and kind of fully fleshed out all its importance and implications, let's see, the global higher form symmetries and gauge theories is the paper by Kyoto, Kapustin, Cyborg. What? 2014. And let me not try to give the most general definition of a higher form symmetry. Let me just give the intuitive perspective that usual symmetries we're used to, at least I'm coming from a condensed matter community, we usually think of global symmetries that act on the whole spatial slice at once. Higher form symmetries, the generators can be thought of as acting or supported on lower dimensional regions of space. So they don't act on the whole space at once, in some sense. So yes, instead of talking abstractly, let me actually discuss an example. So let's talk about Z2 gauge theory. Then basically, if we have the condition that there's no magnetic flux in the system, that's basically equivalent to a certain statement about symmetry. We can say that the system has a magnetic higher form symmetry, magnetic symmetry, which doesn't have a global generator as usual symmetries, but instead a lower dimensional generator. So magnetic symmetry is generated by simply Wilson loops. In other words, if you have some closed loop in space, along this loop, you can calculate the contraintegral of A. And with this condition of no flux basically means this equals 1, right? It's measuring the flux is basically 0. And one can think of this as a higher form symmetry, which acts on this line instead of the whole space. And maybe for those of you who are more familiar with lattice models, let me point out that in the famous toric code model, this corresponds to the plaquette condition. So that the plaquette term, sometimes called BP, if you have the product of sigma z along the plaquette, so along the links of a plaquette, so that is +1, which you can think of as a lattice version of this contour integral of the Wilson loop.
I have a question.
Yes, please.
So you identify the entire phase where the Wilson loop has a perimeter law with this. Perimeter law is not 1. It has some dependence on the size of the loop still.
Yeah, so it's a good question. So actually, when I'm talking about as a symmetry, for a moment, I'm actually in the fine-tuned case where this really is unity.
We're in the extreme deconfined regime.
Yeah, you could say indeed. It's as far away from the confined phase as you can be. First, for a moment, later we'll discuss.
But that's a fragile notion because any amount of coupling will actually
great.
This thing
yes,
decay.
I completely agree. So I'll get there. So I completely agree, but we'll see that the notion I'm talking about is fortunately not as fragile.
Mm-hmm.
But to get there, let's first talk about the fine-tuned case, and then by fully understanding a fine-tuned case, we can see how our understanding is stable from going away to it.
Okay.
But yeah, it's an excellent point. Okay, good. So for a moment, let's imagine a gauge theory where we have this exact symmetry. So in the toric code again, on a lattice gauge theory would be having these exact plaquette conditions. Then it was realized that the deconfined phase or topological ordered phase of the Z2 gauge theory actually has spontaneous symmetry breaking. So,
by the way, Ruben,
yeah.
I think you are focusing on only 2+1D, right? The dimension counting of the symmetry generator.
Okay, up until here, not really, and also this, I don't know, not really actually. This could also be the plaquette in 3D toric code if you wish. I don't think I'm restricting to 2+1D in what I've said so far. Does that sound reasonable?
I get it.
Mm-hmm.
Thanks.
Yeah, this could be a string-like object in arbitrary space. Okay, so the deconfined phase, because also this, we also have 3D topological order for Z2, 3+1D topological order for Z2 gauge theory. So it was basically realized that the deconfined phase you can think of as spontaneously breaking of this magnetic symmetry. Sorry for the ugly handwriting. Spontaneously breaking of the magnetic symmetry. Now, what does that mean? So what it means is that even though, say, the ground state, if I think of the lattice model, has long range order for these closed loops, they're actually equal to unity. This is not the case for open strings. So open Wilson strings have exponentially decaying correlations. And this is true no matter what the choice of endpoint. So we could allow for some arbitrary choice of endpoint operators. No matter what you choose, you're going to find it has exponential decaying correlations. There's many different physical ways of phrasing it, but in the context of symmetry breaking, I would say it's telling us that the disorder operator associated to this magnetic symmetry is not condensed. This is, if it sounds a bit arcane, I would actually point out is the usual way of understanding symmetry breaking, right? If you think of a 1D Ising chain, for example, and if you're in the symmetry breaking phase, even if you're in the cat state ground state, such that the global symmetry is still well defined, you'll find that acting with a symmetry on large but finite regions will have exponentially decaying correlations, right? And you would want to condense the disorder operator to restore the symmetry, essentially. And in the deconfined phase, it's not condensed. And let me actually point out that, so there was already just a question now that having this exact magnetic symmetry is a bit of a fine-tuned limit, but it has been pointed out that this is a good order parameter for the entire deconfined phase if you normalize it properly. So that was pointed out by Fradkin-Shenker and Marku. So there's it has been generalized to an order parameter for the entire deconfined phase. For the whole deconfined phase, this actually traces back to some lattice gauge theory studies in the 80s. Fradkin-Shenker and Marku. That's more like a fun aside. Okay, so the deconfined phase spontaneously breaks the magnetic symmetry. And then the perspective is that the Higgs phase essentially restores it. So if we just scroll back up to this phase diagram, for a moment, if we're on this axis of the phase diagram, then we have it, then the lattice gauge theory model, as I'll discuss more in detail soon, it has an exact magnetic symmetry, and the ground state spontaneously breaks it here, but it restores it over here. So the Higgs phase, Higgs phase restores the magnetic symmetry or preserves it. So in particular, as I just said, having magnetic symmetry means that the open string should also have long range order. So naturally, indeed, restoring magnetic symmetry gives long range order to the Wilson line. But naturally, due to gauge invariance, we need to dress the endpoint. So by Gauss' law, we know that it's only gauge invariant if the endpoints actually carry matter fields. This is really dictated by Gauss' law. Right? If you just had a Gauss, a Wilson string that ends without the matter field, it would not be gauge invariant. And so indeed, the claim is that this is order 1 in the Higgs condensate, and indeed this actually is the conventional Higgs condensate order parameter. Indeed, it's as close as we can get to saying that the Higgs phase is a condensate, right? So in some sense, we want to say that phi dagger phi has long range order, but by gauge invariance, that implies something, at least something like this. But I guess where we depart from conventional wisdom, or maybe, I don't know, or where we build upon it, is we want to stress the point that this should be thought of as a non-trivial SPT order parameter. Indeed, we want to draw the analogy here with, so I briefly recapped the cluster chain, and we saw that the ground state is long range order for some string operator, which condenses the disorder operator for one symmetry, and the endpoint is charged under the other. So what essentially is going on here is exactly the same, that we have long range order, we've condensed the disorder operator for the magnetic symmetry, but its endpoint is charged under the global matter charge symmetry, or whatever you want to call it. So that brings us to the two symmetries that we want to care about here. So we have magnetic.
I have a question about
cool. Can you say again?
In general, will decay exponentially as a function of distance?
Yes, yes, I completely agree. No, yeah, you.
It doesn't obey clustering. It doesn't go to. Doesn't behave like an order parameter.
Yeah, no, I completely agree. So, you're kind of jumping ahead. But
so in what sense is this an order parameter of anything?
Yes. So the precise claim is that as long as you're in this fine-tuned axis, it's an order parameter, and
Yes.
tuning away from it explicitly breaks part of the symmetry. But we will see that this doesn't destroy the SPT properties, and this sounds counterintuitive, but I will get there.
Okay.
You're completely correct to ask these questions, and I'll indeed discuss this. So the precise claim. Okay, let me first make the claim. So if we have the magnetic symmetry, let's call it W for the Wilson group, and we have global charge symmetry. P. So what we see is that the disorder operator for W has long range order with an endpoint that is charged under P. This is the usual story, actually, for decorated domain wall condensation that generates SPT phases. It's charged under P. So, in other words, we can say it's an SPT protected by W and P. But of course, as the question is already showing, what do we precisely mean by this? Because this is certainly it seems like a subtle statement, right? For at least two reasons. Firstly, I mentioned this higher form symmetry, W, but this is only a symmetry in a fine-tuned limit. So am I only making a fine-tuned statement that would? The second subtlety is, okay, it requires also this global charge symmetry, but isn't that a special case of the gauge symmetry, right? Or it'd be weird to say that we're protected by something gauge. The subtlety about the first one was like, is that stable? Because indeed, in many condensed matter contexts, we usually think of SPTs protected by global symmetries. Convention. There have been, to be clear, there have been studies before about higher form SPTs. But yeah, it's not really a much explored concept, I would say. Okay, so to address both of these subtleties, let me discuss what are actually the observational physical implications of this statement, right? What is the clarify these issues of having these symmetries or not. And indeed, my claim is I'm not just making some fine-tuned statement, to be clear. So we'll actually gain some additional insight into this connection between Higgs and confined field. Okay, so what are the consequences? Right, because talking about the consequences also clarifies the well, think about our edge modes, right? SPTs are all about edge modes. So I need to and let's first discuss the case where we have the magnetic symmetry. Okay, and then as just discussed, as long as we have magnetic symmetry, then we will have long range order in the Higgs phase for this open Wilson string. Particularly then the endpoints, of course, have matter fields. Now, we already discussed long range order in the bulk. So this kind of looks like an SPT string order. But suppose we now have a boundary. And suppose the boundary respects magnetic symmetry. By which I mean the Wilson line can freely end there. So in particular, with a boundary, we can actually consider a Wilson line with a single endpoint. Is there a question? Oh, it sounded like it was a question. I think it's not. So what's the significance of this? Well, first of all, the claim is that this is a local order parameter. Unlike the SPT string order in the bulk, in the presence of a boundary, such an SPT string order can become local because the string can end at the boundary. So local order parameter. And why is this interesting? Well, first of all, note that it's gauge invariant. But secondly, it is charged under P. So P was my notation for the global symmetry. And indeed, the claim is that in the presence of a bound, so clearly P, the matter symmetry, looks gauge in the bulk, or at least at the very least, there's no meaningful distinction between the two, right? Like they're naturally, anything that's charged under the global symmetry in the bulk will also be gauge dependent. So it doesn't really seem like a physical claim. But in the presence of a boundary, they're no longer the same. For example, we have these local operators, which are gauge invariant, so they're not charged under gauge symmetry if you wish, but they do carry global charge. If this sounds fishy, I'll explore it in a moment in a more complete lattice model. But this is the general picture. And so this is a local order parameter. And one can argue that since the string order has long range order in the bulk, this local order parameter will have long range order along the edge. In other words, we have spontaneous symmetry breaking at the edge. Okay, so in the Higgs phase, the claim is that it's in Higgs phase for Z. Let me first discuss Zn gauge theory, which is indeed what I've been talking about in this case of this Wilson loop symmetry. The claim is that the boundary will spontaneously break the global Zn symmetry in spatial dimensions D2 and up. It turns out one can make a similar statement about U1 gauge theory, which spontaneously breaks U1, the boundary, for spatial dimensions 3 and up. And so let us first note that this already makes a natural connection with this kind of, this claim that's sometimes made is that, I'll get to this question in a moment. The claim, right, that I mentioned, that started off in the beginning, that sometimes said that the gauge symmetry is spontaneously broken in the Higgs phase. And this is showing that, well, it is kind of true, but only at the boundary, and the boundary is physical. And here it also kind of, you can be connected to some previous literature that sometimes these asymptotic symmetries people talk about, can be kind of connected to this, but instead of working at asymptotic infinity, which feels a bit subtle, it is more concrete to work with an actually finite boundary, and then we can kind of see it all play out. And I see Daniel actually raises his hand, but let me quickly mention that I wanted to mention that actually Daniel and Oguri have a paper from 2018 where they actually also study gauge theory in the presence of a boundary, and they also point out that the boundary actually has, or in some meaningful sense, seems to have a physical symmetry on the boundary. And then we kind of point out that this symmetry is indeed spontaneously broken. But then you had a question or a comment?
Well, I was just wondering, so so partly you just answered. I was going to ask whether your boundary was far away or it was infinitely far away, or you're working in finite volume. If you're working in finite volume, do you really expect these phase transitions to be well defined and sharp? I would have guessed that if you're in if the boundary is finitely far away, then there are no sharp phase boundaries at all.
Yeah, okay, that's a good question. So I guess the way I usually think about phases is everything is finite, and then I make statements about things that are true for arbitrary large systems, right? Like taking the thermodynamic limit, but of a finite system never working directly in the thermodynamic limit. And so,
well, the difficulty here is that
that is not true. Phase transitions only happen in the infinite volume limit.
Yes.
There are no singularities otherwise.
Yes, I agree. I agree with Eduardo here.
Can't you consider a semi-infinite system?
It doesn't matter. It's still infinite.
What? That is a phase transition, right?
Yeah, you could have a surface phase transition in that case, but then the surface is infinite.
No, but if you have the boundary of a semi-infinite system, the system is infinite. There could be a phase transition in it, but then you get properties along the boundary.
I suspect
that's not what the discussion is. A question: if you take the system to be in finite volume, then there is no phase transition, as we all know. You need to be in the.
But why do you have to take it to be a finite volume in order to have a boundary? You can have a boundary with an infinite volume.
You can have that. This is true. You can have a surface phase transition. There's no problem with that.
Yeah, but I'm not sure that this order. He hasn't said exactly what the order parameter is, but my suspicion is that to get an order parameter that has a non-analyticity as a function of where you are in the phase diagram, you're going to have to take the boundary that line is attached to be infinitely far away.
Yeah, I think I disagree with that. And indeed, like Bert was saying, one can consider like a half infinite geometry where one has a boundary, and then we really have a local order parameter that has long range order along the boundary.
Yeah, but I think as long as that line has finite length, I don't see how you can tell. So you keep using the word Higgs, and I probably would have used the word confining to talk about these situations. But I mean, to tell whether that that thing is producing a flux tube with a linear potential or something like it or not, I would have said the line needs to be infinitely long in order to tell whether or not that's creating a state of finite energy or not.
The boundary can be infinitely long. You don't want to be a finite distance from it.
But to tell whether or not we're trying to diagnose what Eduardo calls the free charge phase, right? And what free charge means is that you can have a charge state under what he's calling P that has finite energy and infinite volume. That's what you're trying to diagnose, right?
Well, I'm trying to diagnose actually the Higgs phase, not the free charge phase.
Well, you're trying to tell one phase from the other. There are only two phases. So,
well, I mean, okay, we already know there's a bulk phase transition, so I'm not so much focused on that, but I am trying to show that the Higgs phase still has something non-trivial rather than being completely featureless. In particular, in the presence of a boundary, the Higgs phase will have edge modes, whereas the confined phase will not actually.
But so are you okay? I thought you were trying to diagnose this phase boundary in the middle of the diagram. Are you trying to do something that only makes sense on the left side?
Yeah, so I'm not trying to distinguish deconfined from Higgs. Like I'm happy to take that for, as in that is not the focus. What instead I'm trying to do is trying to ask the question, okay, what is the Higgs phase? Is there something non-trivial? And in particular, is there something there that is qualitatively different from the confined regime?
But I learned, what I learned from Eduardo's paper is that the answer is no, because those two
great.
phases are
Okay.
continuously connected.
Yeah. Okay, great. So this is perfectly the segue to exactly the next comment I'll make. So maybe I can, yeah, I'll let me turn that to now, and then yeah, can see if you're happy or not. So okay, good. And I think there's also a good time to address Eduardo's earlier question or objection or concern that I was talking about this very fine-tuned limit, right? That Eduardo pointed out that okay, only along this axis do you have exact magnetic symmetry. And okay, maybe we can believe that there we have edge modes. At least that is a claim that I just made or tried to make. But then that seems like it might just be some very fine-tuned statements. And now let me turn to that. Is that true or not? Okay, so well, the claim it's not is because we can actually show that this edge mode is perturbatively stable. So what is the upshot? Let me first make the claim, and then it can kind of give the reasoning. But so just to make the claim clear, the edge mode I just talked about, so there's symmetry breaking at the edge, is stable to explicitly breaking this magnetic symmetry by tuning away from this special axis of the Fradkin-Shenker model. Stable to explicitly breaking magnetic symmetry. Okay, and of course, Daniel makes a good point that we all, we are familiar with this beautiful phase diagram. So let me reiterate here, this is the usual and of course correct phase diagram. Let me just quickly repeat it. But the claim would be that this is the phase diagram for periodic boundary conditions. There are no boundary effects. But the claim is, okay, let's now ask about open boundary conditions. What is the phase diagram then? Of course, all the bulk physics won't really care if there's a boundary somewhere. So let me just quickly copy the labels from the left. But the claim is that in fact, there's a whole region where we have edge modes. And there's a well-defined line where we have a boundary phase transition. And note that this is wholly consistent, of course, with the Fradkin-Shenker model, because there in the bulk, there is no transition, but there has to be a boundary phase transition. So kind of give some extra information about this model. Yes, basically like Bert was saying, you can imagine, for example, studying the half-infinite system, and you would find that even though everything remains short-range entangled with periodic boundary conditions, if you study the half-infinite system, it doesn't remain short-range entangled. There's actually a critical state along the boundary for some region of parameter space. And so this addresses hopefully the concern about, are we talking about a fine-tuned feature? But why is this stable, even if the symmetry is not stable? Because this is unusual if you think of standard SPT phases, where we think of global symmetries. And for global symmetries, it's true that if you perturbatively break a global symmetry, you can immediately gap out the edge mode. But the claim is for higher form symmetries, the edge mode is actually robust. And the intuition in hindsight is kind of clear because it's at low energies, it's kind of hard to effectively break a higher form symmetry. But maybe to give a more concrete insight, the nature of the edge is that it spontaneously breaks the global symmetry. Now, if you explicitly break the higher form symmetry, that doesn't allow you to immediately gap out the symmetry breaking of the global symmetry, right? P is preserved throughout. It's only the Wilson loop symmetry that we break. So that's why the edge mode actually is stable, and that's why you need to go through a boundary criticality to destroy the edge mode. Okay, I think Xiaogan, you had a question or comment?
Yes. I wonder whether this phase diagram depend on the boundary. That is, if you choose different boundary, this blue line may shift.
Correct.
I wonder if you choose some very strange boundary, the blue line may be shift very close to this vertical line. Then, Then it's very hard to say whether this is the bulk property or boundary property. I wonder what's the situation here.
Yeah. That's a great comment. So I would say the robust statement is that there is always an open region around this axis where you have an edge mode, but precisely where the and I think actually it will hug this critical line always. But where exactly the blue line happens, indeed, that depends on a fine-tuned choice. Here, this blue line I drew is for, in some sense, a canonical, like a natural choice. If you would write down a Fradkin-Shenker model with a particular type of open boundaries, there's a natural Hamiltonian you would write down, and this is the phase diagram for that. But I agree, right? Conceptually, nothing prevents you from tuning the parameters at the boundary quicker than in the bulk, right? So you can arbitrarily shift it if you're willing to do that. But the claim is you'll always have some open region. Yeah.
That seems to suggest that this property is still property of a vertical line, I mean Higgs phase, which somehow extend to the with open set to the bulk.
Yeah, I'm okay with that. Yeah, but then that's true. It's really the SPT property. Let me say it like this: the SPT is only well defined on this axis, but its implications are robust in an open region. So I completely understand. I agree.
Yeah. Thank you. Yeah.
And yeah, thank you. And maybe one, actually, there's a useful language that has been introduced, not in this context, but in a different context. But it's we can say that the Higgs and confined phases, the Higgs and confined phase are distinct, not distinct SPTs, because the confined phase explicitly breaks one of the symmetries, but you can say they are distinct, something called boundary obstructed topological phases. So this is a terminology that has been introduced recently in completely different context to study some, just a completely different condensed matter thing. But it's a terminology introduced to actually, just give a name to this scenario where two phases are adiabatically connected with periodic boundary conditions, but not with open boundaries. So I think it's introduced, by Eslam Khalaf and collaborators in 21. Of course, it's just, the name, but it's convenient. So we can say the Higgs phase and confined phase are distinct phases in this sense, but it's a boundary feature in some sense.
I feel that maybe using emergent symmetry is easier. So basically, the symmetry here is only emergent in the bulk, but only on the boundary they became exact. So you are talking about. So the SPD is protected by the emergent symmetry or some approximate symmetry in the bulk.
Yeah, you could try to say it like that. Yeah,
that's phenomena you'll see. Yeah. Okay.
Yeah. Yeah, I'm happy with that. Were there some other questions? There's some hands raised.
Yes. Is this so? The claim is this true for any symmetry group?
Great.
Group, whether it's discrete or continuous.
Great. Yeah, good.
Does it work for SU3 or something like that?
Right. It's a good question. So for Zn and U1, it works. For non-abelian, I don't know if Ryan wants to make any comment. I know I would not be able to make a comment. But
so a group like SU3 is not going to work for this because since it's simply connected, there's not really like a magnetic symmetry.
Right.
But maybe something like SO3, have a Z2 kind of SPT for the magnetic symmetry there. It certainly works for U1, but yeah, non-abelian is a little bit.
So for U1, okay, where the matter field is charged in the fundamental representation.
Yeah, charge one, right.
You claim that this will still be true.
What was the last part? The claim is then?
That in the case of U1, if the matter field is charged in the fundamental representation, namely charge 1, you still have a boundary phase.
Correct. For three spatial dimensions and up, So one dimension bumped up by 1 relative to Zn.
Okay, I assume you're going to characterize what the boundary state is, but
good. So the remainder of this talk so there was also while I write it, I see some other raised hands. Please go ahead if yours. Maybe not. So I guess this talk, Ruben, was scheduled for like an hour and a half. I guess usually I stop after an hour, but I can just quickly write down the things I can talk about. Doesn't mean I have to talk about all of them. So one option is to talk a bit more, make a bit more precise what I just said more hand-wavingly, right? What precisely, in what sense does the boundary break it in the case of Z2 lattice gauge theory, where we both have analytic results and numerics? A more general perspective is about the anomaly structure of the SPT phase, which naturally ties into the anomalies known for symmetry breaking phases. And thirdly, the third part would be just to, probably I'll skip this out, but just to mention that there are other probes, even if you don't have an edge. Right, so for everything I talked about was if you have a gauge theory with an edge. But this might, depending on your circumstance, it might sound a bit academic. When do we actually have a gauge theory with a hard edge, right? But the claim is actually there's other probes. So there's ways of making meaningful that the Higgs is a non-trivial SPT, even if you don't just have a hard edge to look at. There's some stuff I could say about that. Yeah, I don't know if there's any preferences for what to look at in the remaining time.
It would be nice to see an explicit example.
Okay. So this bit more discussion about the lattice gauge theory, correct? Look at that. 1 second. All right. So let us consider Z2 lattice gauge theory in 2+1 dimension. Of course, it's a very rich topic, right? Tracing back to Wigner, Wilson, Fradkin-Shenker, etc. So I won't try to write those references. So the setup is we consider a quantum model with qubits, spin halves on the sides and links of the square lattice. And for convenience, I will label the link qubits with the usual Pauli matrix notation, and the side qubits with capital XYZ. But they're both just spin half Pauli matrices. Okay, and then naturally, in Z2 lattice gauge theory, we have an exact Gauss law that we're going to enforce. So basically, what we have is for the matter, we have X and then sigma X. So sigma X is somehow the electric field, right? And X is the matter occupancy. So this is some kind of discrete version of the Gauss law. Okay, and then what is the Hamiltonian? Naturally, the usual Hamiltonian people write down. So for every vertex, we have basically a sigma X for matter, which you can think of as a chemical potential for matter if you wish. And then for every plaquette, we have the tiny Wilson loop. And then with those two alone, we would stabilize exactly the deconfined phase or toric code, if you wish. And then we can also, this is maybe finally answering Ruben's earlier question, what do we mean more precisely by these two axes of the Fradkin-Shenker model? So one axis is the matter fluctuation, which is basically the hopping of matter. So for every bond, it's like an Ising term for the matter sites, but they're minimally coupled to a gauge field, if you wish. Okay, so it's like a discrete version of a hopping, a kinetic term. That's one axis of the Fradkin-Shenker model, and the other one is basically explicitly breaking magnetic symmetry. It's dynamics of the fluxes, so also for every bond. So I'm leaving indices implicit. I hope it's clear. For example, Z sigma Z is, for example, the 3 neighboring sites on a bond, etc. Maybe, is there any questions about the definition? In case something is not clear, please speak up. Okay, so the two symmetries that we'll be particularly interested in is the global matter symmetry and in the special case of H equals 0, we have this Wilson line symmetry, which is just, for any closed loop on the lattice, for bonds along that loop, you can have sigma z, and this latter one is a symmetry only if H is 0, right? It corresponds to, some path like this. If we have sigma z in every link, that commutes with the Hamiltonian if H is 0. Okay. So the usual approach for exploring the phase diagram is that we first realize that we don't really need to explicitly keep track of matter. Well, the usual, it depends a bit on the treatment, but one useful thing is that, okay, there's a circuit. In modern language, you could say Control Z for every nearby pair. Again, on the lattice, I mean, so I can do Control Z on these 2 qubits, on these 2 qubits, on these 2 qubits, on these 2 qubits. And the point of this circuit is that it disentangles matter and gauge fields. Okay. So suppose we're doing it with periodic boundary conditions. Then the circuit is fine.
Is it the same as fixing a gauge?
Say once more.
Is this the same as fixing a gauge?
It's a good point. So it's equivalent to using the gauge fixing to get rid of matter, but or equivalently, it's equivalent to also defining gauge invariant operators, which is possible for discrete case. Yeah, they're all kind of equivalent, but
this is equivalent to go to the unitary gauge or the London gauge, you may call it. Is it equivalent?
I think this is the unit. Well, let's see. Getting rid of matter, I guess, is a unitary gauge. Yeah. So but if you think about it, I won't use that language, but it's equivalent. So the way I think about it is if I conjugate the Gauss law by this circuit, one can check that instead of having this complicated 5-body term, it just becomes a single side term. So for every matter site, we just have X. And now X is +1. So clearly, we've disentangled matter from a gauge field, and now the Gauss law just fixes matter to be +1. So clearly, we don't need to keep track of that. And then the remaining Hamiltonian will be purely defined on the link variables. So in particular, if we use the Gauss law to get basically the upshot is as follows. For every vertex, we have the vertex term, sigma x, sigma x, sigma x, sigma x, the paquet term. So clearly we recognize this is the toric code so far. And one can check that the circuit essentially makes the hopping term into just a single side sigma z, and also the flux term a single side sigma x. So in other words, we see that now it looks like toric code in a field. And its phase diagram has been studied before. Of course, there was the original study, Fradkin-Shenker, but since then also been numerical simulations, so we know precisely where the critical lines are. In particular, a paper by Tupitson in 2008 and others. So here's the 2 axes, and roughly 0.3. There's a critical point, and it looks almost straight, and then has like a little wisp. There's an interesting multi-critical point that's not fully understood. There's a first order line, and then there's some Ising criticality, and then there's gap beyond that. And in this language, we can indeed see that the Higgs phase and confined phase can be adiabatically connected because it's just rotating a single side field from this limit to this limit. And in particular, everywhere here, it seems like a product state, right? So, but it sounds maybe a bit surprising because I was telling you it's an SPT phase, but actually it's not, because we use this circuit, and the nature of SPT phases is that they can be trivialized by a finite depth circuit, right? That's why they're not as robust as topological order. You can, any SPT, there's always a finite depth circuit away from triviality. But the catch is, of course, for example, if you have boundaries, these kind of non-on-site unitaries can be very subtle, right? This works well with periodic boundary conditions, but as soon as you have open boundaries, just like with the cluster chain, this no longer implies that the state with open boundaries is the product state. It's only for periodic boundary conditions that you can do it. Okay, so this is the usual phase diagram, but the claim is that we have an SPT phase More precisely, the original model, right, before you do this circuit, the actual lattice model with matter, the claim is that this is a non-trivial SPT phase here, protected by the global matter and this Wilson line, and that the edge mode it implies is robust, as I was showing before. Let's work our way towards that. Let me first discuss the SPT phase. In particular, it's instructive to go back to the original Hamiltonian before we kind of did the circuit. So let's look back at this. And let's try to get some insight into a particular limit. Let's go deep into the Higgs phase. Let's go this to infinity. Right? So that's all the way over here, if you wish. Right? So let's take H to 0, G to infinity, just to get some insight into the model. What we essentially get, right, is that there's two terms that survive. That we have this, obviously, because we're pinning it, because the prefactor is infinity. That means it doesn't commute to this, so we can forget about this. And it doesn't commute to this, so we can forget about this. So we only have, yeah, and actually this already implies this. So this is the only non-trivial one, together, of course, with the Gauss law. So the upshot is, in this limit, the ground state is characterized by two stabilizers. So stabilizers, the QI nomenclature just refers to many-body operators that leave the ground state invariant and that kind of uniquely define it. It, of course, is invariant under the Gauss law. Obviously. And we have this bond variable, right? Z, sigma Z, Z. But this is exactly the cluster, the 2D cluster state, 2D version of the cluster state on the so-called Lieb lattice. And this is indeed known to be a non-trivial higher form SPT, or just higher SPT, protected by the 0 form P, so it's a global symmetry, and the 1 form W. And this goes back to Yoshida, 2015. He then discusses in the Higgs context. He just studied that lattice model with these two stabilizers. And yeah, kind of pointed out that it's a non-trivial SPT phase. In particular, indeed, we have a non-trivial string order parameter. So let me just zoom in on a piece of the lattice. This looks like Z, sigma Z, sigma Z, sigma Z. So it's basically, you know, some very much like the 1D cluster chain. It has long range order using this 1 form string. So this is a non-zero in the cluster.
Sorry, there is no boundary yet, right?
Yeah, so far not. Yeah, so far I'm just focusing on the bulk. So great, thanks for the segue. So let's now discuss. But what it does already show you from just knowing that whatever the physics is, it has to be equivalent to treating it as an SPT phase, tells you there should be an edge mode. Of course, it's a bit of a high-level argument, but at least the audience member, kind of the audience members that are familiar with SPTs might appreciate that point of view. But nevertheless, let's look a bit more detail with open boundaries. And here we have a choice of how to terminate our lattice. A natural way that I'll prefer here. So let's suppose our boundary. So as Bert was saying, it may be natural to consider the half-infinite system where we just have a 1D boundary and all the rest is infinitely large. What I'm going to do is I'm going to end the system with links sticking out. One advantage is that the Gauss laws, you know, all nicely fit. So we don't have to like ask what we do with those matter size that don't have the usual Gauss law. It's actually not strictly necessary, but it is definitely just a smoother, how to say, easier ride. So we still have a well-defined Gauss law, even for matter sites near the boundary. So we have these rough edges sticking out. Okay. Now, what's interesting about this boundary, this was actually already pointed out in the paper by Harlow and Oguri. well, okay, maybe not, at least, how to say, not necessarily in exactly the following description, but the upshot is somehow the same, that with open boundaries, the global symmetry is not identical to a gauge transformation. So let me say it like as follows. Clearly, the product of Gauss laws over all vertices has to equal unity, right? That's the Gauss law, essentially. Now, what is the product of Gauss laws? And it's x, sigma x, sigma x, sigma x for all vertices. Now, what does that look like? So for periodic boundary condition, that just gives us prod x, right? Because every bond appears twice. But with open boundaries, like the above geometry, let me just write it again. For every and let's suppose this is the edge. For every link in the bulk, sigma x will appear twice and square to 1, but not for the boundary links. So the upshot is we get product of x on all the sides, and we get sigma x on the boundary links. So in other words, this equals p. P was a product of x times sigma x on the boundary links. In other words, the global symmetry P is not gauge, actually is by definition, it's x in the bulk. And that apparently equals sigma x on the boundary. Okay. And this is not just automatically 1, right? So the point is there's a physical symmetry left over. Of course, we could break it. That's, any physical symmetry you can break. That's kind of just confirming it's physical. But depending on the boundary conditions, you could preserve it. And the point is, if you preserve it, you will have edge modes. So the claim is indeed that this is spontaneous. Let me also point out that this boundary action also you can find in Harlow. Okay. Though the question of the phase diagram in the presence of boundaries was not the object of study there, at least not in the context that we're studying it here. So the claim is that this will be spontaneously broken at the edge. And let me first make the picture, and then we can get some analytic insight into it. So if J and G. Oh, sorry?
Is that a gap boundary or gapless boundary?
Yeah, so for Z2 gauge theory, it'll just be a finite degeneracy along the edge. So it's not gapless. The U1 analog would be gapless because of Goldstein's, like they would have a Goldstein mode on the boundary.
Another way of saying this is that there is an obstruction in going to the unitary gauge globally.
Can you just repeat, sorry?
That there is an obstruction in going to the unitary gauge globally. That you cannot really get rid of the matter field in a sense.
Yeah, I would say indeed that.
Because you are left with a global symmetry now.
Yeah, I think that's correct. Yeah, it has some remaining action. Yeah.
Right.
Okay, so just put the face diagram. So here on this axis, we have an SPT. So there, the boundary will definitely spontaneously break the symmetry. I can discuss that more, but actually, I think one thing that may be more interesting to one can look actually at this whole J equals infinity axis, where G is still non-zero. And it turns out along this line, we can also exactly solve the model. And we can rigorously show that this whole region has symmetry breaking up until G equals 1. So obviously my axis is not in scale. And then you can show that at G equals 1, the boundary will undergo a critical point beyond which the boundary is unique. And then numerically, we check that this whole region. So again, these two lines are like where we have an analytical handle. I'll explore maybe one of the last things I can say is I can show how you show this analytically. And then numerically, we check that this whole region, like using the DMRG simulations, we check that this whole region has edge modes with a boundary critical line. We don't quite know if it ends at this point or at this point, but okay, it seems to do something like that. So this line is from DMRG. So sorry, that's some tensor network simulation. Maybe I can comment on how do we know exactly that this line has the general edge modes. So it's quite simple. We can do, so remember for periodic boundary conditions, we had this nice Control-Z gate that we did to simplify the Hamiltonian. We can do that again. You know, we can do Control-Z, 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 da-da-da. And it will still have the same effect of all Gauss laws kind of being thrown out, but it will have the byproduct of changing the action of the global symmetry. Let me just write down the Hamiltonian. Instead of saying all these words, let me just show you. We again get the toric code terms, sigma x, sigma x, sigma x, x, plaquette terms. But now the key point that's different is that we still have the single side term, but it's not for the boundary links, right? Because we didn't have hopping here. We didn't have z, sigma z, because we only hopped from matter side to matter side, not from matter side of the system, which is equivalent to preserving global symmetry. So nothing prevents you from writing that down, but if you enforce products globally, you cannot write that down. So we don't, so B not on the boundary. And then if you again, say, consider the limit of J going to infinity, the net result is to pin all the sigma Z plus 1 fields in the bulk, and you only have the boundary links left over. So if a 1D chain left, 1D spin a half chain left over, which from taking the original plaquette terms and putting in the pinned value of sigma Z, the upshot, sorry, just for, I think because I want to wrap up, what we have left over is a sigma Z Ising term, which comes from this. And then we have this term also, the term that's explicitly broken with magnetic symmetry. In other words, we have the 1D quantum Ising chain. And of course, we know exactly that as a critical point that h equals 1. So that's how we got this point here. And then we numerically check that, that's extended over this whole region. Okay, maybe I see the time is up, so let me wrap up. So one thing I didn't have time to discuss is the anomaly structure of the SPTs. And also, how do you probe the Higgs phase? Like, how do you probe that the Higgs is an SPT phase if you don't have an exact boundary? And here you could connect it to actually something that condensed matter physicists are well familiar with, basically the Josephson effect. And we would argue that you can also reinterpret the Josephson effect as an SPT phenomena, essentially. But yeah, sorry, I didn't have time to go into that. So let me just wrap up with the conclusions. So we see that the Higgs phase, or try to argue that the Higgs phase is an SPT. One perspective is that you can think of the gauge theory as a special limit of an SPT, where one of the SPT stabilizers is infinitely large, and we call it the Gauss law. And the Higgs phase is then the symmetry preserving case. And what does it buy us? Well, conceptually, it kind of gives maybe a more precise notion of the intuition that the Higgs phase in some sense has some symmetry breaking, and makes precise that it happens at the boundary. It also kind of adds insight into the connection between the Higgs and the confined regime, right? That indeed it is possible to connect them because we've explicitly broken a symmetry protected, but at the same time, we can add some insight into seeing that the edge structure is non-trivial and there's not a boundary transition. One thing I didn't have time to discuss is the connection with insulating superconducting junctions in condensed matter. So I would argue that similarly, one can think of the Josephson effect as being an SPT phenomenon. And two other things that if you have a gauge theory with multiple Higgs fields, then everything becomes even more crystal clear. the claim is that different Higgs phases are distinct SPTs. In particular, if you have a spatial interface between different Higgs phases, you would have edge modes there. And then are distinct SPTs, which also can have some relevance to superconductivity. Sorry, didn't have time for that. And then lastly, I guess the more maybe zooming out for a moment, I think where there's like plenty of space to explore more is that it builds a bit of a bridge between SPT and Higgs phases. And obviously, both communities have amassed immense insight over the years. So it can be fun to see how the information flow can go, right? That properties that we associate with SPT phases, we can ask, can we recognize them in Higgs phases? But also oppositely, right? That there's various properties we associate with the Higgs phase. Can those be more generic when we explore the higher form SPT that they're associated with? Or do they require having this exact Gauss law or not? So that could be explored more. Okay, so with that, I guess my hour and a half is up. So I want to thank you for your time and attention and all the fun questions.
Thank you very much. Thank you, Ruben. Question from the audience.
Is it generally the case that the boundary theory has only a global symmetry, or could it have a gauge symmetry as well? So suppose you go to 3+1 dimensions.
Mm-hmm.
Now the boundary is lives in 2 dimensions, not in 1 dimension. Is that still true that is some sort of transverse sizing field theory in 2+1 dimensions, or
good question.
Is it the gauge theory?
Yeah, exactly. Yeah, because in terms of, you could have imagined maybe the boundary theory is going to be 2D topological order or something. So it turns out for this, it's not. Yeah, it's always global symmetry breaking. So the intuition is that it's always the SPT projected by a global symmetry. Okay, let's talk about discrete gauge theory for a moment. The SPT is projected by global symmetry and this Wilson line, but it always intersects the boundary at points. So the boundary theory will have a zero form symmetry and something called a deformed symmetry, some local symmetry. And this is always basically you can think of that local symmetry as being the order parameter of the Ising model. So it always turns out that the boundary spontaneously breaks the global symmetry, at least for these lattice gauge theory models.
So this is, I think, in Bert's terminology, this would have been the analog of the extraordinary phase transition, where the bulk doesn't order and the surface does. There are examples of that in conventional magnets, okay, that the surface orders before the bulk does.
Yeah. I guess that might describe, I guess, this transition, right? Is what you're thinking about? Maybe like, or if you would gauge.
No, that transition is conventional. The other one, the one you described.
Oh, the other one is purely along the boundary. So there's no bulk transition at all.
That is the point. It's only on the boundary. That's why
usually for extraordinary. Oh, I see what you're saying. Yeah, okay. It's like extraordinary where the boundary never does anything. Yeah.
I mean, if the border orders, if the boundary orders, you expect the border, the boundary to order. But if the bulk doesn't order, then the boundary might order, and this is what you're describing.
Right.
This in that field is called the extraordinary phase transition. Perhaps with Navius language.
Yeah, that sounds reasonable.
So, how about the anomaly structure? I mean, in this particular case, you didn't discuss anomalies, but
yeah, the anomaly structure actually very. I think it's very fun. Actually, I can quickly actually it's actually a simple table. The point is that the anomaly structure is very closely related to the anomaly structure that was recently discovered for symmetry breaking phases. So, so if we have the Higgs phase, let's talk about the anomalies, which is basically the SPT, or the anomalies for symmetry breaking. I can talk about Z2 or U1. So for symmetry breaking, right, we have a zero form symmetry, which is the global symmetry that's spontaneously broken, and which gives emergent, it gives like an emergent deformed symmetry, which is a very fancy way of saying that there's an order parameter, right? Like if you have the Ising chain, you can think of the zero form as being prod X, Ising symmetry. You can think of deform as just being sigma Z, right? And of course, for this model, it's fine-tuned, but we know the order parameter is robust. And the claim is these two share an anomaly, which is the reason that the ground state is degenerate, if you wish. Maybe this sounds a bit too like, you know, making a simple thing complicated, but the point is it kind of nicely matches with a recent study by De La Cretas in 19 and Elson Sentel a bit later, which is that if you have a superfluid, you spontaneously break a zero form, and you have an emergent D-1 form, which intuitively, like unlike symmetry breaking, where the order parameter is kind of robust, in U1, right, the order parameter can wind, but the winding is robust in some sense in the ordered phase. And that's kind of related to this, the preservation of that as this D-1 form symmetry. And those two share an anomaly. And in fact, an ELSA paper showed that the supercurrent can be derived from that. Or was it in the De La Cretas paper? I'm not sure. Okay, good. But then now you were asking about the anomalies of the Higgs phase. The main point is, right, for SPTs, any anomaly, any anomalous state has a higher dimensional SPT, which has that anomaly at the edge. And it turns out the Higgs phase is exactly that SPT. Okay, so the Higgs phase has a zero form symmetry. That's our P from before, our global matter. And it has a D-1 form symmetry. This is our magnetic symmetry, if you wish. And these are not anomalous. It's a short-range entangled phase, but they are anomalous at the edge. And indeed, at the edge, right, the dimension of the edge, of course, is D-1. So at the edge, we exactly get the anomaly structure for discrete symmetry breaking. And similar for U1 gauge theory, we have a global symmetry. And in that case, magnetic symmetry is a D-2 form symmetry. And again, the claim is this is anomalous at the edge, which is exactly the anomaly structure of a U1 superfluid. So that's kind of a way of seeing why this is kind of seeing from the anomaly structure why the boundary of the Higgs phase has a U1 superfluid. Does that? I hope that answers the question about the anomalies.
Thank you.
No, thank you. Or John McGreevy has a question?
In the U1 case, in 2+1 dimensions, is there a protected KT phase, like algebraic order on the boundary?
Yeah, it's a good question, right? So I guess you're getting at the fact that this anomaly structure doesn't necessarily imply superfluid. It could allow for quasi-long range order. I guess it's possible it's for 2+1 the 2+1 the edge, which would be zero temperature, would have to be the fine-tuned point, I guess, or to get that.
I think John is right. It's like a KT kind of thing where there's a marginal parameter, and when you break one of the U1s, which is what we're going to allow when we add magnetic fluctuations, depending on whether those vortices are relevant, you'll either disorder the phase or not. So probably there's some region, depending on the Hamiltonian, where you could have some edge stability.
Cool.
But then in the non-abelian case, naively, you will say that this will never happen, that you will always be in the symmetric phase in 2+1, in the 2+1 case, on the boundary.
Right, for non-abelian, I don't have much to say. I guess, Ryan, you were saying earlier, maybe SO3, but I don't know about the stability in that case.
Even if it is SO3, I mean, you cannot break that symmetry spontaneously.
Right. Right. But could you have quasi-long? Because quasi-long.
Yeah, so maybe you expect some kind of WZW model at the edge, and then, right, if you break the symmetry, usually it's just unstable.
Okay, you need something else. Not for a conventional gauge theory, at least.
Yeah, in that case, I'm not so sure. It's more clear to me in 3+1D.
Right.
Well, the 3+1, the edge of a 4+1, or
No, sorry. 2 plus 1
I was
the
asking
edge
about
of
the 2 plus 1
1.
the edge of the 3 plus 1.
Well, then we can break the symmetry, no?
Yeah, there's a nail phase at 0 temperature of 2D, right?
Mm-hmm.
But yeah, maybe Eduardo, was it? Or sorry, Eduardo, were you talking about the 2 plus 1 the edge? Or
the 1 plus 1 edge of the 2
plus 1
theory.
Sure. Okay.
Maybe I would say that theory, if the group is not abelian in general, it will be in the symmetric phase. Now I don't know what we have to do to end up in a WCW in a CFT. You may have to do some gauging or some subgroups or something.
Yeah. No, I agree. And in that case, I would not. Yeah, even actually, if you decrease the gauge group by 1 and dimension by 1, if you look at Z2 gauge theory in 1 plus 1D, a similar thing happens where then it's just a cluster chain. Like the Higgs phase is essentially the cluster chain.
Of course, it's a boundary state.
Sorry?
Yes, there is an edge state in that case. Yes.
Well, but that is fine. Yeah, in that case, immediately gaps out actually if you break magnetic symmetry in the 1 plus like. Correct. So yeah. Similarly unstable.
Taron has a question.
Hey, Taron.
Yeah, thanks for very nice. It's pretty amazing. Yeah. So I have a question about the detecting it from the if you're in the bulk, if you don't have a boundary. You mentioned you will say something about it. Is it that? So I guess I guess is you will, I don't know, again look at some density metrics and maybe charge values or some kind of a entanglement cut. It could be an option, but I guess, are there more rest operators also one can define when you move away from that vertical line? I think someone earlier commented also that, and I don't know whether you can do it when you move away from it. Can you define some renormalized 2-point Wilson, whatever, just some Wilson.
So just to check, is it one question? Are you was the second part asking about the entanglement perspective? I'm
asking about both of them separately. First is maybe detecting it using entanglement, and second is there something else which is not entanglement based, but just some correlation functions in the bulk, which are perhaps some dressed versions of what you had at the vertical line?
In the bulk to detect it's an SPT like thing, or
yeah,
it's subtle, of course. Yeah, because as you know, there is no bulk phase, but something that tells you that maybe the edge is still in the symmetry breaking.
So that's the first thing is maybe easier. The entanglement exposes that edge.
I mean, it's hard to the second part. I'm a bit skeptical of, from related to what Jago Nguyen was saying before, that nothing prevents me from tuning the boundary different than the bulk.
Right.
So unless there's unless you somehow incorporate a natural boundary Hamiltonian in some sense of that word, it's hard to imagine a link. So, but yeah, I can't really say much of that. But for your first question about the bulk detection, the intuition is, suppose you have a gauge theory and you don't want to consider a boundary, right? Because ultimately in condensed matter, right? If you have a superconductor, we don't have a boundary. We have an interface to the deconfined phase, right? If you think of a superconductor, if I have a superconductor with a boundary, it's actually an interface to the deconfined phase, not to the trivial phase, if you wish. So we need to understand, in our universe, we don't have access to a boundary of U1 gauge theory. So what is the analog for superconductors? Well, the analog luckily has been figured out by Josephson, which is you can have a Higgs phase. Let's suppose we have a Higgs phase everywhere, but now I'm going to input an insulator over some region of my space, which means there's a region where I don't allow charge to tunnel. Right, that's the point of an SIS junction, like superconductor insulator superconductor junction, right? We don't allow charge tunneling. The SPT point of view is that what it means is that we don't just have global P preserved, right? P is the prod X or the U1 version, if you wish, for superconductor. But we also have say, PL, right? Matter is preserved on the whole left region. It's a symmetry, right? If you don't allow charge tunneling. So say PL is conserved, right? Because in the absence of a boundary, P globally looks like a gauge symmetry, right? If we don't have access to boundary stuff, it's pretty gauge. But PL, preserving matter only on the left, is physical. Right? In particular, I can write local things like phi, dagger, phi, and some dressed operator is gauge invariant, but it's charged under PL. And the claim is that it's kind of a, even though we don't have a hard boundary here, you can still prove a generalized kind of bulk boundary correspondence or bulk defect correspondence. You can show that if this region is an SPT, then the symmetry acts anomalously on this no charge tunneling defect. So you can prove that this lower dimensional defect actually has a superfluid, if you wish. And that actually allows you to derive also the Josephson effect as a consequence of that. But yeah, the upshot somehow is, the main point is somehow the following, that by introducing no charge tunneling defects, you can probe an SPT, even if you don't have access to the trivial phase. That's somehow the idea. That the Gauss law prevents you from tuning towards a true trivial phase, but inserting a charge tunneling defect allows you to probe the edge modes, nevertheless. I don't know if that was comprehensible. Maybe it sounds a bit.
Yeah.
Okay, cool. Thank you.
In this picture, are these two Higgs the same Higgs phase?
Yeah, exactly. They don't need to be different Higgs phases. If you had different Higgs phases, you didn't even need the insulating part. It could just be, right? Then you would have two different SPTs and there would be an edge mode. But the magical thing is they can be the same Higgs phase and still you have an edge mode if you have this no charge tunneling defect. Which is what the case is for, like, if you think of the Josephson effect, it's between the same, like, you know, you don't have different superconductors. Like, they could be the same material in the same phase on both sides of the junction. Was there another question? I see a hand raised.
When you say no charge tunneling, what's a physical constraint on that?
Yeah. Well, so okay, physically, I would say there's no, you know, there is no hopping of charge. But maybe if you think of a Hamiltonian, let's think of our earlier case of Z2 gauge theory. It would mean that along any link of the, you know, suppose you have the square lattice, right? Any link crossing it, you would have to throw away the Z sigma Z term. You would throw it out. You would throw it out of the Hamiltonian because that would tunnel charge. So that's kind of the physical picture. You don't have tunnel, like you don't have to charge hopping terms across it. And then you can indeed derive that it has a boundary mode or an interface mode or whatever you want to call it. Christian, another question?
Hi, yeah. Thanks for the great talk. Looking forward to reading more about this. I was just wondering if you could, we met, briefly talked at the March meeting, but yeah, I was wondering about the subtleties regarding the boundary. And like in your example, you chose a particular way to terminate the boundary. How much subtlety is there at the boundary in terms of how you choose it, right?
Great. Yeah, it's a great question. So I think the short answer would be, you can choose any boundary Hamiltonian as long as you preserve P and W, like this global matter and the Wilson line. And then the claim is as long as you preserve the boundary, then along this whole axis, sorry, it's a bit cluttered, but this axis that I'm inserting right now, you will always have an edge mode. And you can argue that there's an open region containing it that will have it. That's a kind of universal statement to make. And everything else will depend on specifics. I don't know if that.
Okay, yeah, that's fine. Thanks.
Thank you.
Any more questions or comments? So if not, Hail Egg Product. Thank you very much. Thank you.
Thank you.